Okay, welcome everyone to my continuation of what are my favorite theorems, a biased collection as usual. Today I would like to talk about random walks. So why would I like to talk about random walks? Because random walks. So coin flip experiments, if you want. That's just a random walk. And the topic is whether you're staying or leaving, or well, I got it the other way around, leaving or staying. That is kind of called, I got it exactly the other way around. So transient and recurrent. So recurrent is staying and transient is leaving. So let's have a look actually what that means. It's kind of really beautiful and kind of a lot of beautiful mathematics going on. Kind of a mixture between combinatorics, statistics, and analysis. It's kind of really, really beautiful. So stay with me. So so my first picture is a coin flip walks. So essentially, you have to think about flipping a coin. So what I have in mind is the picture up here. So I just walk on the line, and at every step, let's say I'm here somewhere. At every step, I flip a coin, whether I go left or right. So every step, going left or right has the same probability. So flipping a coin means 50% chance of going left, 50% chance of going right. And then I continue, like something like hop, 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 whatever, right? So you just hop around, and eventually you enter at some point. So here we start at 0, it's kind of the origin. I'm walking on a line, so it doesn't really matter where I start. But anyway, that's called the origin 0. And I go right, left, 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 right. And you could think of this as a heads or tails thing. So if I go heads, let's say I go a step to the right, and let's say I go tails, I go a step to the left. So if I would have something like heads, 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 I would end up at 5. If I would have a tails, 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 I would end up at -5, right? Tails is stepping to the left, heads is stepping to the right. And then I would something like, I have no idea, let's just pick something random, heads, tails, whatever, you would end up heads, tails, heads, you would end up at 1. Right? Heads, tails, heads. That was not really a random choice, but anyway, whatever, you end up at 1. So that's what I call a coin flip random graph. And the question asked, for example, by Polya, we'll see Polya in a second. No, we actually don't see Polya, but we'll get to Polya. Anyway, is kind of the question, we do this, and of course, maybe not of course, but it turns out that in all of these experiments, what you really should look at is kind of the long-term behavior. So we actually look at what happens in the long run. So if you flip my little coin like a trillion times. And the question I would like to address is, how often do we visit a given vertex? So not the vertex, but just how often do we visit the vertex? And let's say, how often do we visit the origin? And it turns out that this is really a theorem of Polya, that in this example, we hit every point infinitely often with probability 1. And here's really the point is probability 1. So that means that's not guaranteed, but it's essentially guaranteed, right? You could be very unlucky and just hit heads all the time. And then, of course, you would never, heads goes me always to the right, so you would never end up at -5, for example. But if you ignore those sequences of coin tosses that actually do not really appear, you will really hit every point with probability 1 and infinitely often. Okay, so we go recurrent, we stay essentially. We will stay at the origin because we will get there infinitely often if you want. It's kind of a nice theorem. So at the random walk, it's kind of the law of large numbers in some sense. So on the random walk here, of a coin flip walk, eventually every position will be hit infinitely often, unless something stupid happens. But in this video, I will like heads. But in this video, I will ignore those stupid cases anyway. Anyway, so it's pretty cute. Yeah, and you can do this in general. Just a random walk on a graph. It's a really good illustration here. So you're not jumping, you're just going one edge at a time. And I'm considering a really easy random walk. So let's say we are at this vertex here, then we would go with probability 1/3. In this direction, we would go with probability 1/3 in this direction, and we will go with probability 1/3 in this direction. So I'm taking what is called a simple random walk. Everything is equally likely. You could definitely think about different situations, But for this video, every edge is equally likely chosen, and I just randomly walk around my graph like this little person here does. Well, I guess this person is rather jumping than walking, but anyway, let's ignore that difference. Anyway, so that's a random walk, and I can do that on any graph. And of course, the graph that we just had was just the line graph, where you can identify that with the integers if you want, right? But we can do that for absolutely any graph. And we ask the question, how often do we visit the vertex? Exactly the same question. And if you think about this, and you really have a finite graph, so like this one here, or the bottom one here. So you're kind of flipping now a coin. It's a very strange coin. It can have 1/3 probability or something, whatever. So you're randomly walking around the graph, and you're asking the question whether you are recurrent. Remember the definition of recurrent. We hit every point infinitely often with probability 1. So we hit every point infinitely often. I will drop this probability 1. There's a fun fact in statistics that a lot of cases are just probability 1 or probability 0 in the long run, and there's essentially nothing in between. It's a 0-1 theorem. Anyway, so every random walk on a finite graph is recurrent. Why is that? Well, I should have said connected finite graph. For me, everything here is connected anyway. Anyway, so why is that? Well, we kind of infinitely often flip a coin if you want, but we only have finitely many vertices. So eventually we hit everything infinitely often. So this question about recurrence is really interesting for infinite graphs, like our integers. And for finite graphs, it's a bit boring. So I'm not saying random walks on finite graphs are boring, but you would study different questions on finite graphs. Anyway, and then Polya, there you go. We finally have Polya. Polya studied the kind of the easiest family of infinite graphs that you can imagine, just the lattice walks in this case. So the one-dimensional lattice, the two-dimensional lattice, three-dimensional lattice, the d-dimensional lattice, and you can just identify that with z to the d, and that's just what it is. And you study random walks, something like this. So you have 3 random walks, a red one, that were computer generated, a red one, a green one, and a blue one. And Polya proved this famous theorem that a random walk in the setting is recurrent if and only if d is smaller than 2. And otherwise, it's transient. So recurrent is here. Recurrent is d smaller than 2, and otherwise it's transient. The d to d equals 3, for example, is transient. And there's this funny, well, kind of mnemonic here. A drunkard will find their way home because a drunkard takes a random walk, let's say on the plane, but a drunken bird might get lost forever, whatever. So recurrent is I hit every point infinitely often, and transient is not the opposite. That's kind of interesting. Or it's not obviously the opposite, because it's saying we hit every point finitely often. And that's not quite the opposite of hitting every point infinitely often, right? So there could be something in between, like you could imagine that you hit certain points infinitely often, or some points only finitely often. But anyway, in this case, it turns out that these are kind of opposites of one another, although they are not. And that's Polya's theorem. So every point is hit finitely many often, so eventually you walk away, and that's called transient. And that happens for the 3-dimensional space, and that's why this drunken bird usually should get lost. Okay, that's really cool. So what Polya showed here is not just kind of a classification of random walks on lattices, whether they are recurrent or transient, very easy condition, but also there are only 2 states, namely recurrent or transient. There's never anything in between, like you go to certain vertices a certain number of times, and the other vertices a different number of times. So there's always just a 0-1 thing. And that's exactly the theorem in general. So every graph is either of those, although they are a priori not opposites, right? So there could be graphs, for example, with probability 0.5 for an infinite in that you hit the, let's say, the origin infinitely often. No, there's not. It's always just it's a 0-1 thing. It's always transient or recurrent, which I think is like a really fascinating type of theorem, but nowadays maybe not completely surprising, because it turns out that you very often have those, and they actually come with a name. They're really just called 0-1 theorems. Like a lot of properties hold with p equals 0 or p equals 1, and you essentially never hit anything in between. But anyway, this is just kind of a meta theorem. And for us now today is just this: for every graph, no matter how complicated, it's either recurrent or transient. And this is pretty beautiful. And people push that, of course, further. So if you want Polya theorem, let's say for Cayley graphs, that's a really, really nice answer. So now we have a Cayley graph associated to a group. And well, you can say group is recurrent or transient if its Cayley graph is recurrent or transient. And you again see the same type of statement. And you can do the following: it's recurrent if and only if your group is finite. Fine, that's kind of the easy case. And for the finite group, so the Cayley graph has always vertices being the elements of the group. So for a finite group, it's a finite graph. And for a finite graph, this problem is a bit boring. Or these are one of our two friends from Polya's theorem, or they are virtually one. So that means they are like a finite extension by a finite group. Sorry, an extension by a finite group, for example. So this classifies all recurrent groups. And it turns out that these are essentially Polya's groups, and there's essentially nothing else. Anyway, so what I've talked about today is kind of these 0-1 theorems in this setting of random walks. And it's kind of really nice. So you either walk away or you stay if you want. It's either recurrent or transient, and you can even classify somehow at least some of the graphs, like the Cayley graphs, that are recurrent or transient. Anyway, I hope you enjoyed this video, and I also hope to see you next time.